Hey everyone. So I'm doing the series on logic and set theory, um, because I think this is easily my favorite field of math, and it's just incredibly fascinating, and the results are so so beautiful, but also so like basic in nature, right? That it's so foundational, and it's just really cool, and it's a shame that not more people know about logic and set theory. So I've titled it Logic of Set Theory, which is vague. So actually, what I should probably be calling this is axiomatic set theory. That what I want to do is I want to develop an axiomatic system within which set theory lives, and then I want to extend it to begin asking questions about the axiomatic system itself. So, you may have seen proofs that certain results can't be proven. I think that a lot of people talk about that, but it's not really well understood what goes into a proof that you can't prove something, and that's the thing I want to attack with this. So hopefully, I'm not going to be going into, because these proofs are insanely technical. So I'm not going to be going into the level of rigor you would need to formalize the sorts of arguments, but I will be going enough I'll be building enough of a foundation and proving enough that you can at least see the line of reasoning that these proofs take on. And we'll see how this goes. But before we even start with set theory, like I said, I want to build an axiomatic system for set theory. So our first goal ought to be to understand an axiomatic system. And to that end, and we'll do this vaguely, right? The whole hope is to build a sort of intuition that we can use to move forward to prove to typically it's a good idea in math, build an intuition first and then extend that intuition into some formal argument. So let's try to build an intuition of what an axiomatic system is and what it looks like by returning to the only axiomatic system that I'm 100% certain every person watching this video has heard of, which is Euclidean geometry. And I think the reason Euclidean geometry is taught in high school is because it's such a simple axiomatic system that it's a ultimately rigorous axiomatic system, but it's simple enough that anyone can be taught it. So I'm gonna let's just briefly, in the interest of review, let's run through quickly the 5 axioms of Euclidean geometry. The first axiom says that given any 2 points, I can connect them to form a line segment. The second axiom says that given any line segment, I can extend it indefinitely to form a line. The third axiom states that given any line segment, I can draw a circle. This is the hard part. What the hell? That was weird. Paint undid I forgot it does that. Anyway, but given any line segment, I can draw a circle with that line segment as the circle's radius. The fourth axiom says that all right angles are congruent to each other. And famously, the fifth axiom, known as the parallel postulate, states that given any line and any point, exactly one line can be drawn parallel to the given line through the point. And so we'll talk a little bit about history, because this is really, the Euclidean geometry is fascinating because it really is the earliest example we have of an axiomatic system. But even back then, this fifth postulate was very contentious. Even back, if you go back and read what all the ancient Greek mathematicians were saying, no one liked this fifth one. And back then they were very Greek mathematics was very intuitionist, right? It was very they they hadn't really formalized the notion of an axiom yet. So a lot of what their math was grounded in facts that they believed were obviously true, that they could just state without giving proof. Really, and that's what an axiom is, right? It's a fact we believe. It's a fact we believe that we believe to be true, but we aren't going to give a proof for, because of course every proof has to rely on a premise, and as a result, you must have one premise at the start to begin with, right? So axioms are necessary, but we won't be looking at it sort of as I believe this to be true. We're sort of going to always look at everything we do as an implication, right? Like, if the axioms happen to be true, then this is what also would be true. That's how we're going to look at it. But in Greek, with Greek mathematics, it was much more, we know that all right angles are congruent, and we don't need to give a proof for it. But interestingly, because of that, there was a lot of controversy about this fifth postulate, the parallel postulate, and in fact, this is an equivalent. That you can prove. It's actually a simple geometric proof that these two things are equivalent. But the original formulation that Euclid gave was actually that given any two parallel lines and given any third line intersecting both of them, the sum of these two angles was 180 degrees. That was the original formulation of the parallel postulate, which was it's so clear, like, at least the formulation of a line and a point, you can draw a line parallel. That feels natural enough. But this formulation that the interior angles of two parallel lines is always 180 degrees is so clearly not a universal truth that a lot of effort was put into trying to prove it, right? So the idea was people would assume these first four axioms and attempt to deduce the fifth. And this was an open question in math for like thousands of years. Was it possible to prove because the fifth axiom was a blight on Euclidean geometry in the eyes of a lot of people, and in fact, famously, this is my favorite little piece of evidence. Famously, Euclid's Elements, right, the book that gives us all this information. Euclid, at the very beginning of the book, he lays out what he calls his like 5 common notions and his 5 postulates. The common notions are like, basically the common notions are stuff like equality is an equivalence relation, things like this, But he lists at the very beginning of the book all 5 axioms, and then he proceeds to prove literally everything he possibly can before finally, at the very end of book 1, invoking the parallel postulate. Or it might have been towards the middle of book 1, but the point is, he delayed using postulate 5 for as long as possible, so that in the event that there was a critic who would read it and be like, okay, I don't believe the parallel postulate, you could at least read the first half of it, and then, you could at least read, the first half of what he says, without the necessity of the parallel postulate, right? But problematically, right? That and it's interesting to read this because there's not much you can prove. Like, you really need the parallel postulate to begin any of the interesting results that we know from Euclidean geometry. Like, it's only very, very basic stuff that you can deduce without the parallel postulate. So anyway, all that aside, I know this is a little bit of a rant, but this is definitely the most significant axiom ever. So it's worth an understanding of this axiom, and then we can apply that knowledge in the future. So the question was, of course, asked, is this axiom deducible from the other 4? And that was an open question for a long time. Many tried, but no proof was uncovered. Until the development of something called hyperbolic geometry. And hyperbolic geometry simply has exactly the same axioms. Simply has exactly the same axioms of 1 through 4. But the fifth axiom, rather than saying, given any line and a point, there's a line segment, you can draw exactly one line parallel to the line. Hyperbolic geometry posits that you can draw at least two lines parallel. And in fact, hyperbolic. This is enough to deduce that you can always draw infinitely many parallel lines, but that's not important right now. The point is, someone created a new axiomatic system that had all of the same axioms, except in effect, it's almost the negation of the. It's almost the negation of the fifth one. Well, like I said, the first Euclidean geometry's axiom stated that one parallel line can be drawn through, and hyperbolic geometry stated that at least two parallel lines could be drawn through. With axioms 1, 2, 3, and 4, you can deduce that you can draw at least one, and Euclidean geometry says you can draw at most one, and hyperbolic geometry says you can draw more than one, right? So, but you don't actually need the fifth axiom to evidence the existence of parallel lines, but in order for parallel lines to be unique or not unique, you need an axiom, right? So anyway, so they developed this field of geometry, and what it is if you aren't familiar with it, it's instead of Euclidean geometry works on flat planes. Hyperbolic geometry is the sort of geometry you would expect on basically shapes. The planes in hyperbolic geometry look like Pringles chips to us, where like saddles, I guess, as well. And if you imagine a point on a saddle, the lines sort of curve outwards infinitely if you try drawing a line. And as a result, you can draw many lines that would not intersect. Given any line, you can draw many possible lines that would not intersect it. So all that intuition, this is actually how it was proven that consider the first four axioms. This is how you would prove that the fifth axiom is independent of axioms 1, 2, 3, and 4. Because we know that Euclidean geometry is consistent. We know that you can't. When I say consistent, we'll get a better understanding of what that means later. But the idea is Euclidean geometry cannot derive a contradiction. You can't use the axioms in Euclidean geometry to derive a contradiction. If you could, if I assume you can draw, if I assume you can draw a circle and you can't draw a circle, the entire logical system breaks apart, right? We don't want conflicting axioms. So we know, though, and this is a very technical thing to prove as well, but we know that Euclidean geometry, you can't derive a contradiction from the axioms. And it was also proven that in hyperbolic geometry, you can't derive a contradiction from the axioms. So now, understanding all that, suppose that someone, and I'll try to use this little corner down here, suppose that someone used axioms 1 through 4, let me use a different color so it's not confusing, to prove axiom 5. Then, right, if they proved the parallel postulate, that would derive a contradiction in hyperbolic geometry, which we said we don't expect, right? Or conversely, if we, in hyperbolic geometry, used axioms 1, 2, 3, and 4 to prove the fifth axiom, that would contradict the fifth axiom. That same proof, the proof would only rely on these four axioms that is shared between both Euclidean geometry and hyperbolic geometry. So, if we have axioms 1 through 4 deriving the fifth in hyperbolic geometry, that would prove a contradiction in Euclidean geometry. And conversely, if you could derive the parallel axiom in Euclidean geometry, you would get a contradiction in hyperbolic geometry. So hopefully, I know I sped through that, but that's actually a legal argument that I've just made there. That's a legal argument that I've just made there to why the fifth axiom cannot be proven And, we'll erase all this and go back to Euclidean geometry. The fifth axiom in Euclidean geometry cannot be proven. And it's interesting, we derived that understanding by considering this magical other fake geometry. But, because this one is equally valid as Euclidean geometry, then we know that the fifth axiom in Euclidean geometry cannot be proven with the first four. So I bring this up because, I think Euclidean geometry is enough of is a system that people are familiar enough with that they could make sense of this. So let's spell this out a little more clear. Now that I've explained both Euclidean and hyperbolic geometry, let's spell out a little clearer how this sort of thing would look. So I don't know the formal name of this, but let's consider something called I don't know the formal name of this, but I'm just going to call it basic geometry. And we have and basic geometry will have axioms 1, 2, 3, and 4. Okay, so the idea is, remember I said Euclidean geometry, that's that thing where, all the planes are flat. We're on the flat grid and all this stuff. Euclidean geometry, of course, assumes that the fifth axiom is true too. But just if we erase the fifth axiom, Euclidean geometry still says that the first four axioms are true. So let's imagine we live in the world of Euclidean geometry. Well, Euclidean geometry is a possible world of basic geometry, right? So the idea is, I have axiom 1, 2, 3, and 4, and I'm saying that's basic geometry. And then Euclidean geometry introduces a fifth axiom. But of course, it still makes 1, 2, 3, and 4 true themselves. So we don't know. Just start with 1, 2, 3, and 4, and we don't know whether 5 is true. But Euclidean geometry is a possible world in which the parallel postulate is true. And then I'm going to struggle to draw this, but like Pringles chip. I don't know. Oh, this is a disaster. All right, well, it would look like this, and then it would slope up in this side. But hyperbolic geometry is another possible world. But in this possible world, axioms 1, 2, 3, and 4 are true, but axiom 5 is not true. And as a result, we know that basic geometry absolutely cannot prove axiom 5. Because whether or not it proved axiom 5 to be true or false, it would contradict one of these two worlds equally valid that we live in, right? Axioms 1, 2, 3, and 4 are still true in hyperbolic geometry, and they're still true in Euclidean geometry, but 5 is different. Okay, so I know that was, I don't know how good of an explanation that was, but I'm just going to run with this. The idea is, this is sort of the key idea, and this is the key idea that underpins the foundational field of math that we'll need to study set theory, and it's called model theory. And, basically, if this over here, if basic geometry over here, let me choose a better color. If basic geometry over here was our theory, then these two things down here, I'll call the models of our theory. And when I get to defining model theory in the next video, I will define it more precisely. But the idea is, if I have a set of axioms, a model of those axioms is a possible world in which those axioms are true. and by studying not only the world we think of. When Euclid wrote down axioms 1, 2, 3, and 4, he was not thinking of Pringles chips. He was thinking of flat planes like we'd expect, right? When he was making these axioms, he wasn't thinking of the Pringles chips. So, of course, when we write down the axioms, we'll have in our head one possible world. We have in our head one possible world when we write down the axioms. But that doesn't mean there aren't other possible worlds out there. And that's the idea. I think this is the key distinction between how we'll be treating set theory and how you would traditionally treat a field of math, right? A field of math will typically, Euclid wrote down the axioms to try to get a handle, to try to study Euclidean geometry. But what we will do is, instead of trying to write down the axioms of course we will write down the axioms that agree with what we think set theory is, instead of just studying what we think set theory is, we will consider multiple possible worlds in which these axioms are true and study all of them. And by understanding how the worlds we study in set theory are different, we will understand the limits, we will understand precisely the limits of the axioms we have. Okay, so I think that's a good concluding point for this first video. Next time, we will begin studying model theory, trying to understand it, probably through the lens of, it's always helpful in math to start simple and then build. And next video, we'll be studying model theory from the simplest possible theory, which is propositional logic. So anyway, thank you for watching, and I will see you in the next video.